Yeah. So the velocity is gained by both the cycle and the person who is riding it, right? So the contingent will be half mv square, and v is same for both cycle and the rider. So m will be both mass of both the cycle and the rider. So that is the useful energy that's being brought out, but there will be some amount of heat energy because there's a friction between the tires and the road. But the amount of energy that heat will be could be less, very less.
Okay, sir.
Yeah. So question number 8. Transfer tips when you push a huge rock, but it does not move, fail to move. Okay. So one thing is you'll get heated up. You will get heated up. Uh, okay. The thing they're trying to ask in this question is work done is force into displacement, right? Displacement is 0. So the work done has got wasted. So the work done, which is being wasted, or the work done is 0. So it'll go into increasing the temperature of the person. So the bioenergy is getting converted to heat energy. Question number 8.
Sir, but sir, you're saying that the displacement is 0, sir. That is about the work, but they're asking energy, sir. So how is that energy and the work related here?
See, basically, you will feel tired, no, if you do this thing. So obviously, bioenergy is getting converted. Okay, bioenergy is lost, so that will appear as heat. Let me Google it. See, from conservation, we know that the energy can neither be okay, that's fine. While pushing a huge rock, there is no transfer muscular energy to heavy rock. The energy is instead converted to heat. Okay, making the body hot, so there is no movement. So since the displacement is 0, there is no useful work done. So whatever energy you spend, so bioenergy is being spent, that will heat your body. Obviously, your palms will get heated up because the friction between the palm and the rock. Okay, that is one way. Other is also you'll get heated up.
Okay, sir.
Heat is one of the easiest way to dissipate energy. It's not a great question, but just for concept clarity. Okay.
Yes, sir. Got it, sir.
A certain household consumed 250 units of energy during a month. How much energy is in joules? So you should know what energy is joules. Unit of energy is joules, which is same as energy is same as unit of energy is same as unit of work done, which is same as force into displacement, right? And unit of work done is joules, and unit of force is Newton, and displacement is meter. So Newton meter you can write in short form as joules, and unit of energy is also joules. Okay, and there is one more unit for energy which is defined as 1 unit, which is defined as 1 kilowatt of. Another thing is power. Before going to this, I'll define power. Power is rate at which the energy is being spent. So energy divided by time. So it is joule per second. So this I can write into another unit as watt. Like Newton meter combination, I'm writing as joule, right? Similarly, joule per second combination, I can write as watt, another unit. Okay, 1 unit of energy is defined as 1 kilowatt spent for 1 hour. Okay, so this is written as 1 kilowatt hour. So this unit of energy, kilowatt hour is also unit of energy because kilowatt is unit of power and H is hours is time. So power into time is energy from this thing. Because power is the rate at which the energy is being spent. Okay. So here the question is 250 units of energy. So that is how many joules? So 250 units. Same as 250 kilowatt hour, because 1 unit is 1 kilowatt hour by definition. So the meaning is, if I spend a power of 1 kilowatt for 1 hour, the energy consumed is 1 unit, or it's same as 1 kilowatt hour. 1 kilowatt is same as 1 unit. So 250 kilowatt hours, if I convert to joules, okay, kilowatt is K is 1000. So watt is nothing but joule per second. And hours, if I had convert to seconds, in 1 hour there are 3600 seconds. So now second and second will cancel. So this will be energy in joules. Left hand side is energy in units. This right hand side energy in joules. So this will be 225 into 36. So 10 cube is here, and 110 is here, and 100 is here. So total will become 10 raised to 6 joules. 25 is 100 by 4 into 36. So this will go 9 times. So it's 900 into 10 raised to 6 joules. This is question number 9. 900 into 10 raised to 6, that is same as 9 into 10 raised to 8. This I can write as 9 into 10 raised to 8. That is the answer. Okay, so the important thing is energy can be, the SI unit of energy is joules. Okay, so and power is rate at which the energy is being spent, so energy divided by the time. So joule per second. Okay, that I'm writing as short form as another unit watt. Okay, and 1 unit is defined as, this is the definition, this you have to remember. 1 unit is defined as 1 kilowatt power being spent for 1 hour. Okay, so in other words, 1 unit is same as 1 kilowatt hour. Okay, so in the question, and actually this kilowatt hour is unit of energy, because it's kilowatt is unit of power, and power into time is energy. So unit is unit of energy. So 250 units means 250 kilowatt hours, this unit of energy. And kilowatt to, if you convert to watts, will give me 1000 watts, and watt is nothing but joule per second. Okay. And hours, if I convert to seconds, I have to convert everything to SI units. That will be 3600 seconds, because in 1 hour there are 60 minutes, and 1 minute there are 60 seconds. So it will be 60 into 60 seconds, 3600 seconds. So this second and second will cancel. So if I simplify, I'll get 25 into 36, and then 10 cube is there, and 110 from here, and 100 from here, so it will become 10 raised to 6 totally. Okay, and 25 I'm writing as 100 by 4, and 4 will cancel this 36 as 9. So 900 10 raised to 6, that is same as 9 into 10 raised to 8 joules. Okay. So the electrical meter in the house measures the energy in units, because it's a convenient unit. That's why they use this concept here. Unit is nothing but another unit of energy, which is equal to 1 kilowatt hour. So 250 units means 250 kilowatt hours. Okay. So 5 more minutes. Do you have any doubts? Or should I go to the next question?
No doubt, sir.
No doubt, sir.
Okay. Yeah. Okay, let's just stop with this last question, question number 10. a mass, the object of mass 40 kg is raised to a height of 5 above the ground. Okay, potential energy. The object is allowed to fall. Kinetic energy halfway down. So just try this question. So this is the Earth's surface or the ground. Okay, object of mass. It's at a height of it's 40 kg at a height of 5 meters. This height is 5. Potential energy by definition is mgh. Okay, m is 40, g if I take it as 10, and the height is 5. So 5 4s are 20, and then 2 more zeros. So this many joules. That is the potential energy at this point, at the highest point. Okay, so now the object is allowed to fall. So somewhere it will come here in the middle. Okay, this will be the height of 2.5 meters because it's halfway down. So this distance is 2.5. Okay, so in the second case, let me call it P2. Okay, that will be mg h2, where h2 is 2.5. So mass is 40, g is 10, and it is 2.5. So it's half of this one, the previous one, so it'll be 1000 joules. And the kinetic energy at this point, the kinetic energy at this first point will be 0 because the object is allowed to fall, right? That means I'm just dropping it. Okay, so here in this case, the kinetic energy will be 0. So the second case, kinetic will be some value, which I can find by using energy conservation. So initial energy equal to final energy. There is no work done. There is no external force. Okay, so this is my initial condition where the thing is at a height, and final condition is it's the midway. So initial energy is the mgh, which is 2000. Initial potential energy. Final energy is the final potential energy, which is 1000. Plus the kinetic energy at the second point. Okay, so from this, I get the kinetic energy when it's halfway down is 1000 joules. Find the kinetic energy when it's halfway down. Question number 10. 1000 joules. What they've asked. Find its kinetic halfway down. That's the only thing. First thing is what is the potential energy? First part. Potential energy is 2000, right? Potential energy is 2000, and the kinetic energy halfway down is 1000. You can also Google the answer, you get the same thing. Okay, any doubts? Shall we close or should I solve this one? This trivial question, what is the work done?
One more sum, sir.
Yeah, 11th one.
So 0, sir.
Because the force and the displacement are perpendicular. It's moving a circular path, no? Satellite. This is the Earth. Okay, satellite is here.
Thank you, sir.
So it's moving a circular path. Okay, so the direction of the force is along the gravitational force between these two. So it'll be along the radius, and the displacement is tangential. So property for circle, the angle between the radius and the tangent is 90 degrees. So the displacement are perpendicular. So work done is F into S, where S is the displacement parallel along the direction of the force. Perpendicular displacement is 0. The work done is 0. Question number 11, right? it's 0. Justification is a perpendicular displacement. 12. Can there be displacement of object in absence of any force acting on it? Yeah, if you have a
No, sir.
if you have a mass moving, it's, see, I can give a, say this is a smooth surface, say ice surface, there is no friction. I just give an initial impulse, initial force for a short time, and then I remove this force. You'll gain some velocity u, right? So after that, you'll keep on moving because the friction is almost 0. So the initial velocity, so since the F net is 0, whatever is the initial velocity, you will keep on continuing. F naught is 0 means F is same as m into a, right? So E is 0. So if initial velocity is there means you will keep on continuing with the same velocity. Yes, there can be displacement for uniform in the absence of any force. Suppose an object is moving at constant velocity, net force acting on is 0, but displacement of the motion is 0. Then there can be displacement. It's exactly the same thing I said. Right. I'm just giving, okay, force is just acting for a short time just before it starts moving. After that, I'm removing that force. So with that force, it has got a velocity u. And since there is no net force acting on it, if I use F naught equal to m into a, acceleration is 0, so the velocity will continue to be the same. Because there's nothing to reduce it. No, there's no force to reduce its velocity. So here the displacement is possible without any force acting on it. This becomes the initial condition. If initially u is 0 means it will not move. But initially there is some velocity. After that, there is no force. So the initial velocity will keep on continuing. Okay, we'll close now. We'll close. Get ready for your lunch.
Yes, sir. Thank you, sir.
Bye.
Thank you, sir. Bye, sir.
Thank you.
Thank you.
Thank you, sir.
Yes, sir. Bye, sir.